Good evening, good morning and good afternoon. A very warm welcome to our first plenary session. This session is a very special session. This contains a special lecture called First ISET Samshir Prakash Distinguished Lecture, which will be given by Professor Stokoi. Formal introduction will be given by our chair and co-chairs. And the other lecture would be given by Professor Adrian. And we are very thankful to both of them. This is really odd time for our distinguished speakers, but they kindly accepted and delivering lectures. Before I hand over my session to Professor S.K. Prasad, who will be the chair of today's plenary session, I would like to briefly introduce about him. He is a well-known personality in India as well as abroad. He has vast experience. For the sake of convention, I'm just briefing. Dr. S.K. Prasad is the professor and head of Department of Civil Engineering at Vidya Vardhaka College of Engineering, Mysuru. He is having over 35 years of teaching and research experience. He obtained his bachelor degree in civil engineering from the University of Mysuru, securing first rank in 1982. Master degree in Geotechnical Engineering from Indian Institute of Technology, Kanpur in 1985, and doctoral degree from University of Tokyo in Japan in 1996. He was a visiting assistant professor at Asian Institute of Technology, Thailand for January 2006 term. He has published over 160 technical papers in national and international journals and conferences, guided over 70 master dissertations, and guided 3 doctoral students. He has completed several sponsored research projects from JSS, MFE, AICTE, and DST. His areas of research interest are in earthquake geotechnical engineering and in performance-based design.
Thank you, Professor Jaka.
Thank you, sir. Just I will introduce our co-chair, then I will hand over to you, sir. This session will be co-chaired by Dr. Indrajit Pal, I.I.T Thailand. Dr. Indrajit Pal is assistant professor and chair in disaster preparedness, mitigation and management, Asian Institute of Technology, Thailand. Dr. Paul, having more than 18 years of experience on research, teaching, training, advocacy, consultancy, primarily focused on disaster risk governance, hazard and risk assessment, risk perceptions, participatory DRM, public health risk, GIS, and remote sensing in DRM and climate change adaptation. Dr. Paul has published number of books and research articles in referred journal, national and international journals. Dr. Paul is member of Board of Directors for the Global Alliance of Disaster Research Institute, Japan. With this brief introduction, I request Professor S.K. Prasad and Dr. Indrajit Pal to take over the session and continue. Thank you, sir.
Thank you very much, Professor Jaka.
Thank you.
I'm extremely happy that the two speakers, Professor Stoko and Professor Roderick Marek, are here. I'm also very, very happy to have Dr. Indrajit Pal here. Please, Dr. Indrajit Pal, give me opportunity to introduce Professor Stoko, and I request you to summarize at the end. Okay. Well, good. Let me take pleasure of introducing Professor Stoko. Good morning, or should I say good early morning to delegates from America and Europe. Good evening to the delegates from South Asia. And good late evening to the delegates from East Asia and Australia. It's an honor for me and to my colleague, Professor Indrajit Pal, to chair the first plenary session of the 7th International Conference on recent advances in geotechnical earthquake engineering and soil dynamics. We are sincerely thankful to the organizers of the conference for the opportunity provided to us. We all know that earthquake geotechnical engineering has evolved over the last 6 decades tremendously. The understanding of wave propagation through the soil has always been a serious challenge, even today, considering the complexities in soil, heterogeneity, inhomogeneity, nonlinear behavior, pressure level dependency, strain level dependency, strain rate dependency of soil, and the randomness of earthquake wave are among a few of the complexities which make the assessment of vibration at ground surface very challenging. If at all, we have achieved some understanding in this direction, the contributions of Professor Kenneth Stocco are considerable. I'm proud to present Professor Kenneth Stocco from University of Texas at Austin to the delegates of 7th ICRAG. Professor Stocco does not require any introduction. However, for the sake of completeness, I wish to briefly introduce him. Professor Kenneth Stocco has been working in the area of field seismic measurements, dynamic laboratory measurements, and dynamic soil structure interaction for more than 40 years. He has been instrumental in developing several small strain field methods for in situ shear wave velocity measurements. He has also developed 2 types of resonant column systems that are used to evaluate dynamic soil properties, dynamic rock properties in the laboratory. Over the last 14 years, Professor Stocco has led the development of large-scale mobile field equipment for the dynamic loading of geotechnical systems, foundations, and structures, an activity that's been funded by National Science Foundation in the NEES program. NEES stands for Network for Earthquake Engineering Simulation. The equipment has already led to the development of new testing methods to evaluate soil nonlinearity and liquefaction directly in the field. Professor Stocco has received several honors and awards, including election to the National Academy of Engineering, the Harold Money Award from the Society of Exploration Geophysicists, the Eugen Togler Award from American Society of Testing and Materials, and Bolton Seed Medal, and the Carl Terzaghi Distinguished Lecturer from the American Society of Civil Engineering. That the title of his talk today is The Increasing Role of Surface Wave Measurements in Site Characterization. I'm also very pleased to mention that this lecture is the first ISET Shamsher Prakash Distinguished Lecture. Sir, you have 40 minutes time. I'll remind you 3 minutes before. The platform is yours now. Please go ahead, sir.
Thank you very much for that very kind introduction. It is basically 1 a.m. in the morning my time here in Hawaii. So I'm wearing a Hawaiian shirt, no tie, but I am happy to have 2 grandsons with me who are making sure that everything runs smoothly. But we're having a good time here. However, I very much look forward to giving this lecture, and I hope there are some interesting points that I can convey to everybody. Okay, this brief outline. Look at body and surface waves for field seismic measurements of shear wave velocity, overview surface wave measurements using, the SASW method, spectral analysis of surface waves, one that we use a lot. Present a number of examples that will hopefully give you some ideas and some concluding remarks. One other thing I just would say quickly, the National Science Foundation from the United States is happy to work with other countries. We've been in New Zealand for one, and help develop other people's capabilities with this type of equipment. So if you send me an email or something like that, I don't want to be inundated, but there's we would be very happy to interact with you on developing such type of equipment, and you can see if it's worthwhile to you. Okay, and a couple concluding remarks there. Okay, just talk about field seismic methods, and I want to make one very important point. So the cross hole, 30 years ago, it was used a lot because it's a very fine measurement technique. The waves stay more or less, you know, most of the time we have horizontally layers or slightly inclined. So the waves are in there, and something happens that you don't realize that's the benefit. So when you use initial arrivals is what they do, and you see the spacing is only 10 feet, 3 meters between boreholes. But you use the right frequency content, give you the right wavelength that works properly for the measurement, okay, with a good impact. When you start talking about downhole methods, now things get a little more complicated. It can be traditional seismic CPT, seismic DMT, dilatometer measurements. But now if you start going into the waveform, you're going to get a waveform that's much too long for the layers you feel you're identifying, and you will not get correct numbers. PS suspension logger. So when we come down here to this one, you can see that it's 1 meter spacing between sensors, and that's where they're measuring. You need to use very high frequency. I'm not sure that's always done, but it is used a lot in the United States these days for maybe drilling one deep hole and logging that. And finally, the thrust of my talk is surface waves. And I'm an active source guy with all the big equipment, but passive sources are also used and work very well. But we can do some very deep testing with active sources. And they can even go deeper with passive sources at times. But in all of these techniques, wavelength is an important factor. And in the body wave measurements, 1, 2, and 3, wavelengths are typically ignored. Not good. And I'll show you why, but using surface waves. Okay. Just the other thing is, when you start looking at this, you start looking at the material that's sampled. So let's just say that this is a borehole right here, the vertical one right in the center, up and down. You can see where the downhole, it'd be like 2 or 3 meters away. And it's this zone that you're looking at going along that borehole. If you look at the PS logger, it's between those 2 horizontal blue lines where the cursor is going around right now, where they make a measurement. So it's a really, really fine resolution measurement, but now how it translates to earthquakes and earthquake responses is sometimes of concern. And finally, surface waves, and I'm just going to show you 2 different spacings because it's between receivers that we make measurements. So here, this 15-meter spacing will basically, and you'll see why in a little bit, give you this zone down there that you have sampled well. The 30-meter one is going to give you this zone down here, sorry, with the longer dashed black lines. And you build basically a pyramid that's up near the surface and then gets wider the further you go. But if you worry about lateral variability, you'll see that we use surface waves, shallow measurements, and maybe multiple points. Okay, next. So here's the overview of surface wave measurements using SASW, and you see down there in the bottom of the slide, the spectral analysis of surface waves. And whenever I talk about surface waves, I'm talking about Rayleigh type waves. Some folks will use love waves. We don't see them used that much in engineering, much more in geophysics. But we're going to talk about Rayleigh waves. And the key to a Rayleigh wave measurement is the keys. You need a good source that generates the frequencies, hence the wavelengths that you're trying to measure. And you need calibrated, well-acting receivers. And a 1 hertz geophone, by the way, I'm sorry, I'm going to talk in terms of Fahrenheit. but and I've never seen anybody say these sort of things, but we've learned it the hard way. When those geophones that have big springs in them and so forth get to be above 90 degrees, really 92 to 93 degrees Fahrenheit, sorry, they begin to warp and they lose their calibration. We even have ice packs that go over them, little coats that go over them in the desert when we're out there in very high temperatures. Okay, that's an aside, but just to keep you alert. So the surface wave method is based on surface waves, Rayleigh waves, and they have the strain distribution that looks like this. Okay, and so basically that would be one wavelength, and you'll see it here again shown on the surface in a minute. But it's mainly this part of it, about the upper half of the wavelength, that really samples the material and gives you a good measurement. So you need to make this wavelength would see the upper part of layer 1. This wavelength right here would see the lower part, the upper and lower part of 1, maybe a little bit of 2, but you're going to build with longer and longer wavelengths, deeper and deeper that you sense. And that's the whole idea. And so you're trying to, your forward modeling is going to be taking out the surface layers that you have measured and know the velocities, and then continuing on to deeper layers where you are able to evaluate those velocities with longer and longer waves. Okay, here we go. And this is showing that dispersion measurement. So we have a site over here, 3 layers, velocity increasing with depth. This first wavelength, higher frequency, is going to generate a phase velocity through that material that's here. This next one, and there are going to be hundreds of these, but the next one is going to go lower, so it's going to see this surface layer and some of the lower layer. The lower layer is increasing velocity, so the overall phase velocity that moves with is going to be higher. And the idea in the field is to get this wavelength versus phase velocity, and it's going to be wavelength versus frequency in the field curve, and it's a dispersion curve. This is a normally dispersive. That means everything is increases. With depth, we don't have inversions and so forth, just to make a simple case. All right, so, and the testing we do, we use a common midpoint. And that common midpoint or center line is shown right here in the white. And we would place a receiver there. That's a middle receiver. You're always working in receiver pairs because you're determining the phase shift between the 2 receiver pairs. So here's receiver 1 and receiver 2. They are spaced at a distance X. The source is over here, and it's also spaced at a distance X from the first receiver. Then you see the second receiver pair, R2 and R3, and those are 2X. So this is for the shallower part. This is for the deeper part of collection at that array. But you can see that for the second pair, the source to the first receiver in the second pair is 2X. So you're always keeping the distance from the source to the near receiver in the receiver pair equal to the distance between the receivers, 90% of the time at least. But that's a general testing approach. This would show, you know, you're just starting here with short spacings. And let me go backwards, excuse me, because one thing I didn't mention is you can have an impact source, you can have a random noise generator, you can have step sinusoidal vibration. I'll show you all 3 of those. Okay, so we have our center line, we have short spacings, we then, the biggest spacing there is 2X, then we make this 4X here and 8X and so forth, and you just get larger and larger spacings. You're going deeper and deeper until you run out of energy, until you can no longer generate energy that will propagate that far. It all depends. I mean, okay. Here we're now looking also in the last 4 or 5 years, lateral variations. So this is just a special arrangement. It is very nice for us where, okay, we start out with the short spacings, and then after some distance, we have, so here, this would be the last of the short spacings, it's 2x. Now here it's doubled, so we're going deeper. Here's 4x. Here's 4x there between those two receiver spacings. Here is our normal R2 and R3, that's 8x. But we add a fourth receiver, so that's 4x and 4x. I'm talking about the spacings between the receivers. So now we have three zones, three vertical planes that we're looking at, and we can see how the dispersion, each one of those planes is the same or different. And that's the way we look at lateral variability, sloping ground, and things like that. So it's always changing. People are always making improvements in this. Okay, active sources. On soil, when you first start, so here we are in A, there's a sledgehammer that the guy's just hitting down. That's an impact source, got lots of frequencies. Receiver 1, receiver 2, receiver 3, like we had in the simple array, 1 hertz geophones. If that was on concrete, they'd be accelerometers, and it would be shorter spacings. But we're mainly talking soil now. So if we want a random wave generator, a bulldozer moving back and forth is an excellent random wave generator. Random wave collection is very fast, so is impact collection. But you know, here would be your 2 receivers, and then the source will be coming within X of the first one, and it'd be going back and forth, back and forth. Sometimes the bulldozer drivers get a little angry with you because they're working very hard, or the machine's working very hard. But it's an excellent source, and I'll just show you various projects where we've used it a lot. Then this is our piece de resistance. There's one of these in the world. We call it liquidator. It's a step sinusoidal vibrations, and when you do it, you come from high frequencies to low, and you see over here, that's the start, high frequencies, that's the taper, that's a little exaggerated. High frequencies are getting lower and lower, and down here you'll see that gives you various facts about spacings and so forth. But we typically, whatever the spacing is, we typically have like 100 frequency steps in the spacing. And the longest spacing, let's say the longest spacing was 1,000 feet, 300 meters. That might take a half hour of that machine just turning away to generate all the energy to give you a good record. Okay, so here we go. We're going to look at liquidator used as a source. And this is real data. The sketch above just shows what we have, but this is real data from a nice site, of course. And what you see here is up here is a wave that is exactly 1 cycle from the source to the first receiver and 1 cycle from the first to the second. And this is wrapped phase so that you can see it in the field easily. And what you see, okay, we haven't got any energy here because the normal operation of the liquidator only goes to 1 hertz. And so we start here, but we have to know that's coming back to 0. So we have to collect enough data for that. So here's going to 100, a minus 180 degrees. That really would look best going vertically as a dashed line, because that 180 and the 180 below are the same. And so now you have 180, that's 360 degrees. That's A. The point A is the A wave right above it. That's 1 wavelength. Then this is half of that wavelength. That's a third. That's a quarter. So you are performing QA measurements in the field. While you're doing it, making sure you're collecting good data that's proper for normal analyses. And for point A here, you see the phase velocity, frequency, turns out the frequency is 4.37 hertz. The wavelength, because we know the distance between the receivers, we can be calculating this in the field, huh? And that there is 180. And so the velocity there is 790 meters per second. Okay, I'm going to show you B and C. B is the blue line up here. That's 2 cycles. So there you see 2 cycles. C has got 4 cycles. There's C in that one. And again, and I like this very much, and I'm going to stress it, I'm sorry, because we do NQA1 work a lot, nuclear quality assurance level 1, and there's all kinds of calibrations and things. But you are performing quality assurance of your data in the field when you gather it, and you don't walk away knowing, you either got it or you didn't. And if you didn't, you got to figure out what other things you have to change to get it. So it's extremely helpful. All right. I showed you A, B, and C. This is a phase plot now. So you see a phase plot vertically, phase velocity, and wavelength on the log scale, because you're going to cover so many such a wide range in wavelengths, 10 times what we get in velocity. But that's curve A, that's curve A from the record you saw, point A, point B, and point C. So here we go. I have graduate students, so it may look like a lot of work to color code all these spacings, and it is, but there they are. So all of that's going from very short, less than 2 meters. There's point A, by the way, where it fits in everything that we've got, to the longest wavelength we have here, which is 860 meters. So we would say we've got good data to 430 meters. And we did this in half a day, and all from the surface. You can't get cheaper than that, I can tell you, for that kind of depth investigation. Adrian would even agree with at least half of what I said. I'm not sure all, but that's okay. We're good friends. I see him there, and he's a good fellow. Okay, so here we now do best match and forward modeling. We like to use our head a lot of the time because it can be quite complex. And the match gives us, the match gives us this shear wave velocity profile that you see at the site. And as I said, here we're going to 430 meters, and we did that in half a day. Okay, so that's the basis for the testing technique. By the way, we also are doing, and I shouldn't really say this, spectral analysis of body waves, because you can do a lot of things with body waves and looking at wavelengths too that are very interesting. And you can invite me back at another time and I'll give you more of that. And we're heading towards in situ material damping, and you can identify material type much better with material damping than with material stiffness. So there's still a lot to be done out there, a tremendous amount. Okay, I'm going to give you 4 examples, and do you see them there? That's okay. I won't waste time talking about it. Here's the first thing, Dillon Dam. We needed to know the quality of the alluvium within and beneath this embankment dam. It's in Colorado. That reservoir is one of the best Denver has, the city of Denver, that supplies water to it. But it was going through a reevaluation for earthquake response. And that's why, and it hadn't been done before, and that's why we got involved. And so it's really looking at the general approach of estimating the quality of the material. And here we go. That means we have a reference where, oh, this is good material, that green dashed line. And wow, we measured in the field this, oh, that's great material. Uh-oh, we got a problem here because this is below the good material. And so we got to figure out what to do with that. But below that, we're in good shape. Absolutely, you see things like that. Here's another one. That would be like the dam, for instance. Here's another one that you might look familiar to you. Here's before, and then here's dynamic compaction, dropping the big weight to the Menard approach. And there's the improved zone and how much it improved and so forth. Okay, so here's back to the dam. This is the dam, Crest Road, and we're looking at the downstream face, but only partially up it, and the tow road and the downstream area. So I'll show you some data there. This is saying the same thing, but in cross section. So downstream, we're looking at the natural alluvium. We won't worry about the bedrock. You'll see a fence here, and now that's along the toll road, and right at the toe of the downstream face, and then several in the downstream face. Okay, here we are. Here's the dam right here. If you notice, there's a little road. It looks like that road was built so that this drill rig could go up there and drill. And I can tell you, they got almost nothing out of the drill rig, and you'll see why in just a moment. There's our good random source generator. We only had to go down like 50 meters. It works like a charm. And here's where one of the areas where test pit was developed, and I'm going to show you the test pit. So here's the test pit in that case. And you can see large material. That's Professor Ed Idris digging. I have never seen him do that before, but I asked him to pose doing that for me taking the picture. Don't tell him I said that, Adrian. And here is Dr. Gonzalo Castro, two very fine people that were involved. And this just shows you a general gradation curve. And they tried to sieve it before they put it in the dam. So that's for the natural material, but the material in the dam had that vertical cutoff. So within the upstream and downstream shells, you see on that red line right there, and it's basically half cobbles. And then you get into a lot of gravel and just not that many fines. Okay, so it's a very interesting material. Here are we like to show it this way. Here's a number of profiles that we did in a particular, in the bulk of the area, but not all of them. Here are the profiles by the gray lines, and then here's the COV. In this case, they wanted the mean, not the median, because we normally plot the median. But here's the mean and the plus and minus 64th percentile, and looking at this remarkably low number, 0.1 in the natural material is very, very unusual. And I'll point it out again in another example. But we got very good profiles. The last thing I should tell you is right near the surface, they didn't know what because it's downstream, for the natural alluvium. They didn't know what the contractor did, and there was quite a bit of variability. So the top couple meters was thrown out, and they didn't worry about them. Okay, and what we'll do is we're going to take, well, this shows you, before I was ahead of myself there, this shows you the natural alluvium is in the gray dashed line. The alluvium in the dam and below is shown in the yellow, and here's the dam material. So here's the yellow, that's dam material. And then this is natural in yellow, the natural alluvium beneath the dam. And you see the natural alluvium off to the side. Now, when we take a look at this, we see that here is 3,000 meters per second. So this stuff is basically very stiff, hence it's dense. The compacted alluvium in the dam is similar to the natural alluvium, so it's dense and not cemented. I'll prove that to you in a minute. And there's no loose zone in the alluvium under the toe of the dam that they are worried about. Okay, now, what am I going to prove to you? And you're sort of covering up some of my words, so I hope I get them all right. But this is okay with the pictures. Divided it into 3 groups, not a big deal, just different areas, and we have more than that. But we plotted them like a resonant column test. That means log of shear wave velocity versus log of confining pressure, but now expressed as vertical effective stress, okay? And what you see is natural variability in the wiggles in that, but you see a line drawn through all of that, which says the VS1, so at 1 atmosphere, is 1,245 meters per second. And to go up and down in confining, there's the confining pressure relative to atmospheric pressure. and the exponent is 0.32. This exponent of 0.32 is very reasonable for uncemented gravelly soils. If it were cemented, that gray line would go like I'm drawing here. It would be very flat and it would be very high because of the cementation at shallow depths. So it's not cemented. We can prove that to ourselves. The number there at 1 atmosphere represents a large D50, a large C sub U, that is a large uniformity coefficient. So particle spaces are filled in, so between the big particles with smaller particles. And again, as I said, no cementation and representative of normally consolidated soil with no plasticity. That's what we get by just replotting the data like we would have from a lab test. Okay, is it uniform vertically? And the answer is yes, because now you're going to normalize it. Here we normalize it to VS1 at all depths, just by using the equation I described to you, but now with the right exponent, very important, and with the right number at 1 atmosphere. And so, yep, it's very uniform, and we're happy. Will it liquefy? Well, this is a chart that Ron Andrus really put together as a PhD student at Texas. And it's mainly sands from Imperial Valley. And here's the earthquake cyclic stress ratio. Here's the stress corrected shear wave velocity. And you see that it ends at 300 meters per second. And you see that this is a no liquefaction zone, even though we don't necessarily have, know the liquefaction characteristics of the other material. When we go back and see what V sub S was in that other material, here we have it. V sub S1 is 380 meters per second. Here's about where 380 meters per second, my red arrow on this chart. No, it's not going to liquefy in an earthquake. You know, when you go to some sites like this and things work out, and if the owner's there and they know about it, the owner seems to want to come and give you a hug or something. And I say, are you wearing a mask? No, that was long ago. We didn't have masks. No, you don't need to thank me. Just pay the bills. And we are very pleased to have been able to help you. So it's nice. Other material quality assessments, that was soil. Here's rock. I'm not going to describe it any more than that, but here's rock. And this is a dam. And when the emergency spillway was used, it failed. And they were able to shut the emergency spillway on these gates and go to another 2 places where they had other gates to help the reservoir. And during the rain, they could get rid of enough of the water so that it didn't overtop the spillways. And we were called in much later to evaluate, 20 years later or so, to evaluate the rock and to evaluate the repair they did. They did a good job. We're very interested in rock. I'm working on trying to do an seismic CSD of rock, seismic CQD, seismic SQD, seismic quality designation of rock, and it's going to be on fracturing, and that has effect on attenuation, and we're working hard on that right now. So you can go out and get some very good measurements in rock with this same stuff. That's one of our smaller pieces of equipment we call Thumper, but it generates much higher frequencies, and it worked well with hammers on this rock. Okay, second one, nuclear power plants. Here is the Vogel Electric Power Plant in Georgia, near Augusta, just outside of Augusta, Georgia. They have 2 plants working, and you see 2 new units, units 3 and 4. And the owner, Southern Company, they had a multi-million-dollar, because they had to put in 2 deep excavations and backfill them. They wanted to make sure the backfill would meet their specifications that were used in the design of the power plants that the Nuclear Regulatory Commission, when they applied for the license, They wanted to make sure it met it. And so this was very unusual, but it was very expensive. You know, they had a big investment there. And now if you want a contractor go crazy, if the contractor has to also interact with the professor, the contractor goes nuts. He said, I'm not listening to that faculty member, but I've heard that before. So we just kept working together. But basically, you see, I divided that fill into 4 layers, and that's what I suggested that we would do. And they're 20 to 25 feet thick, 6 to 7.6 meters. And we'd come in once they got at a certain height, like you see there. So after the first layer was put, we'd test it, second layer, and so forth. Okay, so here they're making the excavation. You see the 2 power plants. Here, the backfill is nearly done. And we were testing, you know, around this area. So you see, we could test the whole area, that even where you see concrete in the nuclear island, where it's going to be, because it's filled high enough up here, and there's a retaining wall. So we did each unit, and you see all the piping and so forth. Wow, it is complex. Here we are on top of it once it's completed. Now we did 4. This is the 4th time we went out there and tested at each new site. And to me, this is beautiful. Let's just look at unit 4. This is unit 4 over here. And so that's the first time we came in. So this is the SASW measurements. And what you see, let's maybe look at this point right here, whatever the depth that is below the top. And when they put the next amount of ground on top of that of select fill, it moved from there over to that point because of the loading. That's confining pressure. Then the next time it moved over there because of the confining pressure. And the final time it was here. So you see how you could just watch the material behave. And by the second set of measurements, we could say, don't worry, you're going to meet the specifications you have, and I'll show you what the specifications are in a moment. Are the backfills laterally uniform? Okay, you see how these things are also close together? Yes is the answer. And this is a very interesting number. So here is a man-made fill as carefully as possible, and the COB is basically 0.05. I don't think nature can do any better, but nature does some very good things. But that's a very good number to keep in your back pocket if you do stuff like we do, just to see where we fit, and how variable the site might be. Are they vertically uniform? Yes, this one is. The contractor had to pull out some stuff here, and so that was there. Don't worry about it. But when he put it back, he really got it dense. So we made it a little less vertically uniform. It wasn't a big deal. Okay, I'll tell you another thing about my group up. So here we are. Let's look at unit 4. We're going to take this median profile here in blue. Here it is right over there, just because of the layers that we made it in. But we can fit a resonant column test through it, and you see the slope is the power on the confining pressure. Now this has got silty material in it too, so it's going to be a little lower than 0.25 or 0.26 that you might get for just clean sand. But oh yeah, and so I was asked, well, how well did the lab do? And you know, I didn't answer it correctly, and and they went on to something else. I raised my hand and said, I don't like my answer. And I said that, well, the lab shows more variability, and of course it should, because the sample is this big, that you're testing, and you got huge amount that you're testing in situ. So that little variability that you might find there disappears in the overall scale as long as it's well mixed. Okay. Here's what they had to do. They needed to have the shear wave velocity at the base of the nuclear island be at least 1,000, at least 300 meters per second. And this shows you, here's the base of the nuclear island, and here's the 300 meters, and it's above it. Hallelujah. Here we are in this one. There's the 300 meters per second, and it's above it. Everybody was happy, even the contractor, that placed the fill. Okay, there's dynamic compaction in Taiwan. That worked very well. We did SASW to do this. This is an interesting one in Italy. That's a landslide from that point to about down here is at least a half a mile. And so nature brought that down in heavy, heavy, heavy rains. And the question is, do they have to excavate this, or is it dense enough that they can just start to build on it? And we, with a big, big bulldozer and so forth, we showed them it was dense enough to build on and not worry about. Extremely cost effective, but you couldn't do it any other way. You could not do it drilling or anything. It's not possible. It was such a hodgepodge. But nature put so much energy into it, it was going to be dense. And yes, we agreed with that. Okay, deep profiling on the top of Yucca Mountain. Yucca Mountain was meant to be the first geological repository for high-level radioactive waste. Politics got involved and it didn't happen, but we spent about 5 years working on Yucca Mountain. So here's Liquidator on the top of Yucca Mountain, long rays, even had a telescope to help us, total station to help us space things out there and make walking and stretching cables easier. And here we are. This is where the emplacement zone was going to be down here. Though here are on the top of Yucca Mountain, all of those sites. These were on ridges that are heading down. There also were tunnels put in to investigate the material. So here we are in the tunnel. This just shows you it's quite complex. That's an accelerometer. We'd drill a hole, take a nail, pound it in, put a magnet on the end of the accelerometer, whack, it would stick right there. We had a whole crew ahead of us drilling and pounding nails, and we'd be coming behind. So that's the high frequency stuff in the rock, because you're right on the rock. Okay, here's all the data that we had right here. And you can see now the COV at depth is going to be quite high. Always the COV near the surface, almost always, is high. But that's because these stiff layers appeared in some areas and not others. So we divided into two different groups. Here are, down at the title, you see 9 softer sites in group 1, meaning that it didn't pop out here. But there's the tunnel. You keep track of me on time, please. And the tunnel, meaning, is at the repository level. And yes, we did both of those things, so I don't know if you can trust them or not, but there was excellent comparisons. And this is the same thing over where the stiffer sites were, and the same type of material, but obviously geology did something to it and made it stiffer, but that worked out really well. Okay, here's a water tunnel in Washington, D.C. that failed, and we ended up doing that. It's in rock. And you can see my expertise. It's usually with the hammer, and the graduate students get lost, unfortunately, there, but they deserve all the credit. Here is a mine shaft that was going to go, that was connected to a mining operation that had closed, but there was a big open mine at significant depth, and they were thinking of using it as a pneumatic repository. So they'd pump air into it, have the pressure build up, and then when the power was needed, they'd open up and turn the fans and create pressure out. The wall was fine. They didn't have to do anything to the wall, and we showed that. The last one, am I too far over? The last one, very deep, 500-meter profiling at least. And this is at a greenfield site. That means they want to build a new nuclear reactors there, but they don't exist. Nothing has been done yet. And we did 5 arrays there. Here's Liquidator in normal operation. In normal operation, all the white stuff here and the tires and all of that hold this plate down. And then that weight, which is about 12,000 pounds or something, we excite to generate the forces. And the plate on the plate, and all the white holding the plate down, there are airbags here to isolate the movement of the plate from the truck. It doesn't isolate it, it gives it a good start. And here you see the profiles. This isn't a big site, working out very well, and you see that we're down 300 to 365 meters. Okay, for a long time, I've been fretting over not getting even lower frequencies. And so one night, I think waking up in the middle of the night, I said, okay, I'm going to lift the whole darn machine up, which is a little bit dangerous. We have to be very careful. And we build a footing for it. Someone does that for us. And now the weight and everything there that's not the stationary parts of the machine are fixed, and we use that to push everything else. So it goes from about 12,000 to 60,000 pounds that we're moving up and down. And that causes us to generate waves. We could only go to 1.3 hertz. This is quite theoretical, but only 1.3 hertz at peak force. Now we can go to 0.65. 2 times 0.65 is 1.3. That doubles the depth that we can go to. If we were going to 3,000, now 300 meters, now we're going to 600 meters. And so we've been using that. I don't have the latest data to show you, but whoops, sorry. But here it is. Oops. Here is what you saw in the first one. And this green line, which is a different color in the plot that shows where they are, I'm sorry, is here down extended. And just for your edification, there's at that site the PS logger, and it's shown right here. And you just see that. That's all I'm going to say. But I can tell you, to drill that hole to 600 meters or thereabouts for the PS logger costs more than all of our work we did at that site. So yeah, I'm not sure it was cost effective, but some people might want to see it. No problem. Conclusion: small strain mechanical properties expressed by VS and Gmax play an important role in geotechnical engineering. Small strain mechanical properties are critical in dynamic and static. And I didn't show you static, but we predict the settlement of footings on sand with shear modulus. And it starts out with Gmax. And it tells you that a 1 foot plate isn't very good at all. Okay. Let's see. Continuing evolution, evolving field testing procedures and numerical analyses with Rayleigh type surface waves and log waves form an important and cost-effective way of evaluating V sub S profiles in all times of geotechnical and structural. We do a lot of structural testing, as you saw in the tunnel and so forth, looking out, do a lot of concrete testing. Under all types of field situations, the importance of this work in modulus measurements and shear wave velocity measurements is only going to continue to grow, because it's theoretically solid and it can move forward. And like I say, when we start doing damping measurements, it's going to really have a huge impact on what we know about the material. Okay, Professors Sitaram, Prakash, and Jaka, I want to thank for organizing this conference and inviting me, but I also need to give them a special thanks for allowing me to present the first ISET Shamshir Prakash Distinguished Lecture. And I know Shamshir Prakash, and we've interacted for decades. I must tell you, if Shamshir is listening, I hope you can also think that this talk all came from Professor Dick Woods, who passed away just about 6 months ago, because he was also a good friend of yours. And I'd like you to feel that some of this came from him. Okay, many funding agencies helped us. Texas graduate students, I would be dead in the water without them. Faculty, technicians, and administrative staff. It takes a big crew to run all of this. And thank you so much for this opportunity. I hope I didn't spend too much time.
No, sir. Thank you very much for a very lucid and informative lecture. Though you are in the middle of the night today. Thank you.
And all of these slides are yours.
Okay,
You
nice.
can distribute the slides. It's fine with me.
Okay. There are a couple of questions, and it will be a pleasure if you could answer them. This is a question from Mr. Aniket Desai. Do you agree that MASW test is better than SASW for mode separation? If so,
Oh
why
my
did you
God,
use SASW?
no, you don't even have to finish the question. Not a bit. Oh my gosh. I mean, they tried to, you don't see them doing any nuclear power plants. You don't see them doing any type of testing like this. Yeah, I'm just gonna have to stop there. So my answer is clear.
I understand. Okay, again from the same person. When the length of the receiver array was kept so large to get such high maximum wavelength, how to ensure that the generated waves are reaching properly at the farthest receiver without attenuation, especially for a high frequency wave?
There's huge attenuation to get to the farthest receiver. There's huge attenuation just like in soils. But you know, looking at the data, if it looks reasonable to you, and you will, so you have to move forward with that as a quality check, but that doesn't mean something couldn't be a problem there. And when you start reducing your data, you look at it. But no, this is just the physics of the problem. We're not doing anything with, you couldn't have that long a wave if you couldn't generate that much energy. The earthquake really outdoes us, and we can't do anything like the earthquake. But no, that's, and okay, let me say one other thing to repeat it. So when we're at the longest spacing, that may take an hour of going through those 100 frequencies, but you're adding them up each one many more times than for short spacing. So it's a long time, plus it's a low frequency, but without that equipment, you could not do it. You could not do it. Yeah, because, well, I guess there'll be other ways, but right now I don't know what those are.
Thank you. Thank you very much. And I think, these were the questions. So if audience have any other question, please do post your questions. And it's very nice of you that, in the middle of the night, you are able to, help us with your lucid presentation. Thank you very much from the organizers again. So, yeah, I think, we will move over to the next presentation, next keynote lecture.
I don't want to take any of Adrian's time. I hope I didn't, Adrian, take any of your time.
No, sir. No, absolutely fine. Absolutely fine. Okay. Thank you.
But I apologize, Adrian, because I'm about to go to bed.
Have a good night, Ken.
Thank you, sir.
Okay.
A very fine fellow you have there.
Just maybe one question can I ask, sir?
Professor Jekka wants to, please, Professor Jekka.
Professor Stokoi, very nice presentation, very interesting. And we are partly we are a little bit working on MSW, and Mr. Aniket Desai, he's one who is working on it with us. Sir, I have several questions, but I will restrict to one or two quickly. You have tested wave propagation on the embankment dam as well, which is the sloping ground. So what we assume is wave is propagate vertically downwards, but in this case,
no. You saw with my when I was on the slope, I assumed, and that's an assumption, that the waves were going in perpendicular to the slope. So that little road that I said they built, the dozer would be going like this, and our arrays are parallel to the crest, but we're drawing a line that's perpendicular to that road, let's say, into it. and we let the other folks, the other experts, calculate the states of stress along that direction. We did not do that. We used them so that we could try to get the right states of stress. We might screw it up. So I didn't want to do that. But yeah, no, we assumed that you could take a flat surface and you could incline it, but you'd still be making measurements perpendicular to the surface. And you saw the numbers, it certainly looked that was very reasonable. And given the other information for Professor Idris and Castro and others, there were more. And there were also some geophysicists on the panel. They accepted, they were happy with that data.
Just another last quick question, sir. You have tested landslide as well using SSW. Actually, in case of landslides, usually it is a heterogeneous. It has the boulders, soil, mixture. So whatever you are getting, maybe average velocity, how we can interpret and how we can use it?
Because it tells you that the material between, and so you're right in that we had a big bulldozer. That doesn't mean every place on the line was good for us, because there could be a huge, almost the size of a house, down there that we wouldn't know about. So we would move around to once again QA our data, so to speak. Okay, what it should look like. But even as soon as you start getting longer waves, if you get waves that are 100 meters long, 200 meters long, well, you can't do the house yet, but you still can do big stuff. And that every line didn't work, but enough of them did to allow the other people like Professor Yamakowski, that's who we did it for, very famous person, Leaning Tower of Pisa, so forth, to look at the data and feel comfortable, and that's what they did, and it's worked. I mean, they built what they wanted to on it, and it's been fine.
Thank you, Professor Stokoi.
Okay.
Thanks from organizing committee,
Yeah,
and
thanks.
also kindly joining in the middle of your night. Bye.
Yeah, Dr. Prasad, just a quick one link with Dr. Ravi's question.
Please.
Hello, can you hear me, Professor Stoko?
Yes, I can.
Please.
Thank you so much for this sort of nice discussion and so much of elaboration on the different practical aspects. So my question is slightly linked with Dr. Ravi's question. In case of landslide, how we can use that SSW in case of since we know like it's a quite heterogeneous in the crown and also in the toe. The compaction is very different if when you go by the stratigraphy as well. So in that case, how we can use in terms of the monitoring, you mentioned about the monitoring. So is there any possibility we can use that SASW data for the real-time or near real-time monitoring? Or any example of this? How we can use that data for the real-time or maybe near real-time data monitoring for the landslide?
Now, let me see if I understand the question. Are you trying to look at the situation where failure may be going to occur and you're wanting to detect the failure zone out there, the developing failure zone? Is that your question?
Yes. So that in the critical infrastructure, especially on the highways, if we can predict little bit of early, so
Okay.
that many of the things can be settled. Yeah.
Okay, so by and large, the answer is no. But let me explain why. The answer is we wouldn't see that, because I didn't say this going through, but there's lots I didn't say, because Professor Rodriguez-Merrick has a lot to say, by the way, too. So you would be looking at a softer area. Now it's starting to expand. I mean, it's starting to shear. That's going to make the material softer compared to the other material around it. Okay, we will not detect an inversion. That would be called an inversion, the softer material beneath it. We will not detect an inversion that is smaller than 10% of the depth to the inversion. So if the inversion is at 100 meters down, it needs to be at least 10 meters thick, and 20 meters thick would be better. And it won't be. Your failure surface is going to be too narrow, in my opinion. You know, I'm guessing now, but your failure surface is probably going to be so thin that it will not be seen by that testing technique. By
Okay.
surface. Yep.
Thank you.
That would be a wonderful application, but I'm not living downstream from it, even if I'm running the test. I don't, I'm not going to trust it.
Yeah, similarly, like I was wondering about that MASW, because there are multi-channel, and all these multi-channel can generate different frequencies and depth also, of different wavelength as well. So thank you. You can explore.
Well.
Okay, thank you again, Professor Stocco. Yeah, so let us move over to the next presentation, next keynote lecture. Again, you know, good early morning to good late evening to everybody in different geographic areas. I'm very happy to introduce Professor Adrian Rodriguez-Marek from Virginia Polytechnic Institute and State University. Professor Rodriguez-Marek will be delivering the next keynote lecture in this plenary session for the 7th International Conference on Recent Advances in Geotechnical Earthquake Engineering and Soil Dynamics. Professor Adrian Rodriguez-Marek obtained his PhD from the University of California at Berkeley in the year 2000 in civil engineering. He then joined the faculty at Washington State University, and since 2010 is a faculty member in Civil and Environmental Engineering Department at Virginia Tech. Professor Rodriguez-Marek's research and teaching areas are in geotechnical earthquake engineering with a focus on site response and seismic hazard analysis. His major research contributions are in the areas of ground motion characterization and on the treatment of uncertainties in seismic hazard analysis. In particular, Professor Rodriguez-Marek has contributed to the development of concept of non-ergodic seismic hazard analysis, which implies a more rigorous treatment of uncertainty in ground motion in hazard analysis applications. Professor Rodriguez-Marek's work on characterization of single station standard deviation has been used in various hazard assessment projects for nuclear power plants. Professor Rodriguez-Marek has also participated in various seismic hazard assessment projects for nuclear power plants across the globe, including projects in South Africa, Spain, and the United States. And today, he is going to talk on seismic hazard analysis for critical facilities. Sir, you have 40 minutes time, and I'll remind you about 3 minutes before. Now the platform is yours. Please do go on, sir.
Thank you very much. First, I want to make sure that you can hear me well.
Yeah, you're very much audible.
Okay, well, thank you very much. It's a pleasure for me to be able to deliver this lecture. I would like to thank the organizers for working so hard to prepare a conference under these circumstances. Being a speaker, I could watch firsthand all the work that the organizers have done, and I truly commend you for putting together this conference. I wish we could do it in person, but you have done a great job in dealing with the circumstances. In particular, I would like to thank Professor Prasad for a kind introduction, and to thank Professor Jaka. We have interacted a lot during these times, and I know the effort he has invested in putting together this session. Also, I'd like to acknowledge Professor Sanchar Prakash for, I know he has been instrumental in creating this conference and in bringing this conference to India. He has done a lot to help the profession, so I would like to acknowledge him. It's always a challenge to follow a presentation by Professor Stocco. I seem to have the bad luck to always be in this situation where I'm speaking after Professor Stocky, but it's also an honor, and I will try to abide by that honor. I would like to acknowledge before I start the fact that this presentation is really putting together work that has been done in multiple projects, mostly projects for nuclear power plants. These projects include the project in South Africa for a siting project in Thaispun, the seismic hazard assessment of the Hanford laboratory in Washington State in the USA, a project that involved the seismic characterization of nuclear power plants in Spain, a total of 6 different sites in Spain, and a project that's currently underway that's funded by the Nuclear Regulatory Commission that's looking at the implementation of site response for nuclear power plants. The results or the observations that I'm presenting today are really the outcome of discussions that have taken place in these projects. And in particular, I would like to acknowledge the contribution of colleagues that were common to many of these projects, including Julian Bomer and Peter Stafford from Imperial College, Bob Youngs from Wood Consultants, Linda Natik, who is a consultant, and Professor Ellen Radji from the University of Texas at Austin. A brief outline of my talk. I will present an overview of probabilistic seismic hazard assessment for critical facilities, and a key element of this is the concept of non-ergodic PSHA. And in order to discuss non-ergodic PSHA, we need to understand clearly the difference between aleatory variability and epistemic uncertainty. After this introduction, I want to talk about the role of site response analysis, and in particular, the characterization of epistemic uncertainty in site response, and a tool that contribution that I think it's a simple contribution, the use of logic tree to capture site response, but I think that's very important in order to be able to properly characterize the uncertainty in site response. And part of that uncertainty is also related to model uncertainty. So I would like to highlight some recent work that has been done to characterize modeling uncertainty. If I have to outline two of my objectives, let's say, of this talk, is they start to introduce the concept of non-ergodic PSHA and to discuss how can we properly incorporate epistemic uncertainty in site response into the probabilistic seismic hazard assessment framework. Okay. So the objective of probabilistic seismic hazard analysis is to integrate across all possible earthquake and ground motion scenarios. This means that we take a source, and this is borrowed from a classic from Reiter 1990. We take all sources that are surrounding a site, and we consider for each source a distribution of potential magnitude of potential earthquakes, considering the magnitude of earthquakes that can occur at each source. For each combination of source and distance from the site, we predict ground motions, which is the third step, and we predict ground motions as a function of distance, and then we integrate all possible scenarios. And when we mention scenarios, we mean magnitude and distance, and all possible ground motion scenarios that can occur for each magnitude and distance earthquake. We integrate them to predict a probability of exceedance of a given ground motion parameter. Typically, we deal with mean annual probability of exceedance. The key element of this is that we need to account for all sources of uncertainty. And the sources of uncertainty can be grouped into aleatory variability that deals with inherent randomness and epistemic uncertainty that deals with lack of knowledge. The integration can be formulated using this classical equation, the hazard integral. We predict the mean annual rate of exceedance, which is the hazard. This is what we call the hazard for a given ground motion parameter. And for example, I will use spectral acceleration at any given period. And this is equal to the annual probability of exceeding a spectral acceleration. The integral takes into account all the natural variability of the earthquake phenomena. The probability distribution function for magnitude and distance accounts for all possible combinations of magnitude and distance that can occur that are related to the inherent randomness of the earthquake phenomena. Because it is inherent randomness, this integral, the hazard integral, is capturing the aleatory variability, the inherent randomness of earthquake occurrence. This element, the probability of spectral acceleration exceeding a certain value, is obtained from a ground motion prediction equation and captures the aleatory variability in ground motions. That means that captures the inherent randomness in ground motion predictions, and it must include local side effects. So a lot of what I'm going to be talking from now on is going to be related to how can we capture the local side effects in this integral. The outcome of a PSHA, if you wish, the objectives of the PSHA is to develop a hazard curve for ground motion parameters, in particular, when we're talking about nuclear power plants or critical facilities for spectral accelerations, for a range of oscillator periods. And so here we take a typical range of oscillator periods, and for a range of return periods. So the lower we go here, the more rare the ground motion is, therefore the higher the intensity of the ground motion. And in doing so, again, we need to account for all sources of uncertainty. I'm going back to this. The sources of epistemic uncertainty are, the sources of uncertainty are divided into epistemic uncertainty and aleatory variability. Epistemic uncertainty, this comes from a Greek word, epistemos, that means knowledge, relates to the lack of knowledge. So it's uncertainty that results from lack of knowledge. And because of that, and this is the key for epistemic uncertainty, it is uncertainty that can be reduced with additional data or with further knowledge of physical phenomena. On the other hand, aleatory variability is a variability that's presumed to be intrinsic randomness of a phenomenon. In fact, it comes from the word alea in Latin, which means dice. It's related to that random nature of throwing a dice. In principle, aleatory variability cannot be reduced with additional data because it's inherent randomness. However, additional data can help constrain its value. Separating the two sources of uncertainty is important because you can identify which uncertainty can be reduced if we invest more in the problem. We add additional data or we improve our knowledge of the phenomena. So in fact, this is an important premise of my whole talk, that the distinction of these two uncertainties is important because it allows us to identify where we can improve our understanding of uncertainty, where we can reduce uncertainty. Aleatory variability is captured in the hazard integral. For ground motions, including side effects, this is captured in the ground motion prediction equation, which is implicitly included in the integral, in the hazard integral, in the calculation of probabilities of exceedance of a ground motion parameter. Now, again, this has to include side effects. So the aleatory variability in side effects has to be included in the prediction of these probabilities of exceedance. Epistemic uncertainty. And I have to say one thing. I have reviewed multiple seismic hazard assessments that are done at different levels. When we are working in critical facilities, in fact, regardless of the degree of sophistication of the seismic hazard analysis, aleatory variability is always included. Everybody that has done a PSHA has dealt with the hazard integral, therefore implicitly has accounted for aleatory variability. Not so with epistemic uncertainty. In critical facilities, we take a lot of care of accounting properly for epistemic uncertainty. But I've seen many projects, seismic hazard assessment projects, where there is no such care placed in capturing the epistemic uncertainty. However, it is a key requirement that we must properly capture epistemic uncertainty. And this implies uncertainty that can result from multiple interpretations of available data. Epistemic uncertainty may be present because the data set is not full and it doesn't sample well all the source path and side factors that influence ground motions. Or epistemic uncertainty may exist because some of the scenarios that control hazard do not have a good representation in the ground motion database. Typical way, or the typical approach to account for epistemic uncertainty is to use logic trees. So logic trees present, this is a sample logic tree for source characterization, or actually both, for source characterization and attenuation, dated 1992, but it accounts for possibilities for the different states of nature, if you wish. Okay, so you can have a source geometry that can be long or short. There is a truth, there is a true source geometry, but we don't know. It is a lack of knowledge, and we represent these uncertainties in a logic tree with weights that represent what we think is the most likely, or what's the likelihood that each of these branches represents a true state of nature. So when we do represent the epistemic uncertainty in the resulting hazard, this is represented in fractals. So you have fractals that spread out 5 to 95. A fifth fractal is one that is likely to be exceeded only 5% of the time. 95th fractal is one that's likely to be exceeded only 5% of the time. Often you don't see these fractals. It has to be only sophisticated analysis that see these fractals, but they are important because the fractals represent our uncertainty in the hazard. Typically, what we see is the mean curve. However, the spread of the fractals does affect the mean curve as well. What you see here is typical. At low return periods, at high return periods, the mean hazard corresponds typically to the median fractile. But as we go to low return periods or more rare motions, the mean hazard shifts towards the higher fractals. So a higher spread of fractals also implies a shift in the mean hazard, which is what we typically use. Also noting here that aleatory variability impacts ground motion in the slope of this hazard curve. Therefore, it tends to impact more on the on low annual frequencies of exceedance. Okay. So slope reflects aleatory variability, the range reflects epistemic uncertainty. So a question, and a very important question, is how do we identify what is aleatory variability, what's epistemic uncertainty? And it's not an easy distinction unless the distinction is made within the confines of a model, so within the confines of a parametric space. And this was very nicely stated by Professors Derkjuregen and Professor Ditlevsen in their book. It is the model builder's responsibility to make the distinction between these two types of uncertainty. So if we think about ground motions, which is what concerns us, we know that ground motions are affected by source effect, path effects, and site effects. And these elements are what contribute to source effect for geometry, slip distribution, slip time function, etc. For path, we can look at the velocity structure along the path, attenuation structure, heterogeneities that occur, Moho bounds that affects ground motions. For size, we can look at impedance, damping, and resonance effects. These are affected by layering or by the 2 or 3D structures of the soil, material properties that Professor Stocky has elaborated on this, or the depth of the elastic hull space. But the key is, how do we take all these effects and parameterize? When we develop predictive models for ground motion, we postulate these models within a parametric space, but they have to be parameters that are predictable for future earthquakes. Variations of source site and path that are not included in the parametric space, they become part of the aleatory variability. However, variations that are repeatable, variations in source path and path that are repeatable, but not included in the parametric space, should be epistemic in nature. Because of the fact they are repeatable, they should be predictable. And again, the definition of epistemic uncertainty is that these are predictable uncertainties. So if we look at the source, for example, as an example, we have all these factors that influence the source. However, our models for predicting the source include a parameterization that's relatively simple: magnitude, fault type, deep, rupture width, depth to top of rupture. So we know, for example, that stress drop has a strong influence on the amplitude of ground motions. We know that slip distribution has a strong influence on the spatial variability of ground motion. Yet these are not included in our predictive models. So any variability that results from variabilities in stressor of sleep distribution are part of the aleatory variability. The same can be said of path. Our parametrization of path is simplified into distance measure of whether we are in a hanging wall or not, or whether we are in the back arc or fore arc of a subduction region. Therefore, any variability that results from parameters that are not accounted in our parameter space goes into the aleatory variability. And for a site, it's the same. The site is complex, can be extremely complex, but our parametrization is typically only 1 or 2 parameters. So in fact, these top 2 parameters, VS30 and Z1.0, are the only parameters in the parameter space of the prediction of site effects in modern ground motion prediction equations. Everything else will go into aleatory variability unless they are repeatable. And this is what I want to focus on. So what are those repeatable effects in site response that shouldn't be part of the aleatory variability? And that depends on how the site response is accounted for. There are really 2 conceptual approaches. One approach that has been called ergodic, and I will explain why is it ergodic. It uses the parametrization space from the ground motion prediction equation. So it uses VS30 and depth to 1 kilometer per second, for example, to fully, as these are proxy variables that are meant to fully capture site response. It assumes then that all sites with a similar parametrization are identical. Therefore, any variability within this parametrization goes into the aleatory variability, and we compute this aleatory variability, we parameterize it with the uncertainty in predictions. But because of this, the variability is mixing space with time, because all the variability from sites that are identical in this parameter space in the network gets put into the aleatory variability, the spatial variability. But predictions at a given site over time get put together in the same bucket where we compute the variability. And this is why this is called ergodic assumption, because ergodicity, the concept of ergodicity is that the spatial and temporal variabilities are similar. An alternative approach is a site-specific approach where we presume, or we assume from the beginning, that the site response is site-specific, and we use either analysis, or if in the rare cases that we have data, we use data to predict those repeatable site effects. Therefore, the aleatory variability should only reflect variability over time. This is what we call the single station sigma. And this is what's properly called a partially non-ergodic approach. We are removing ergodicity in site response across a network, and we are computing only uncertainty at a given station. Okay. So we are back to the question, what are the repeatable effects when performing site-specific analysis? And it's actually useful to go back to how we define ground motion prediction equations. A form of a ground motion prediction equation would have a ground motion parameter, let's call it y, typically spectral acceleration. That's a function of predictive variables, which can be magnitude, distance, VS30, etc., and some model coefficients. And this would be equal to some median model that would include site response for whatever parametrization we have in the GMP, in the ground motion prediction equation, and some residual. The residual itself is typically partitioned into a between event term and a within event residual. The event term will correspond to the average residual for a given event, and the remaining residual is a within event residual, which actually can be partitioned further into a repeatable site term and an aleatory variability. And it is this repeatable site term, this delta S2S, the one that we aim to predict in site response analysis. So which are the effects that are going to be repeated event over event at a given location? If we take apply the variance operator to this residual component, we get the components of variability, the between event variability or tau, the site-to-site variability of phi, and the remaining variability, which correspond to the remaining residual, which is what we call the single station phi. In an ergodic approach, all these components of variability are taken together to make up the aleatory variability. Whereas in the partially non-ergodic approach, because we predict the side term, so essentially we are predicting this delta S to S, when you take the variability of a deterministic term that you are predicting, that variability goes to 0. So the single station sigma eliminates this source of uncertainty, and therefore is made up only of the between event variability and the single station peak. So we are reducing uncertainty, but it's really not a reduction in uncertainty. It's a shift in uncertainty from aleatory, the side-to-side variability, to epistemic, because very important, we need to predict the uncertainty in predicting the side. Okay. So why would we do this? The obvious answer is because we have lower values of aleatory variability. In fact, this is research, this is from a publication that, from 2011, where we look at single station estimates of, here I'm looking only at the phi component, at various locations, California, Switzerland, Taiwan, Turkey, Japan. I'm also adding estimates by Lin that were done on a network in Taiwan. All these values are significantly lower than the ergodic counterpart. This is from a data relationship, but it hasn't changed much in the updated relationship by Chu and Yang. And in fact, the uncertainty in phi, the uncertainty of the within event variability goes from an ergodic value of 0.6 to about 0.45 to 0.4 for single station sigma. So it's an important reduction in aleatory variability, which means for low return periods, you get much lower current motions. But because another reason to do this is because if you are doing site-specific analysis, you are predicting the side term, then therefore, and you are predicting the uncertainty on the side term, if you don't use single station sigma, then you are double counting uncertainty. So it's important to be aware of this to avoid inflating the uncertainty. Now, we are using lower values of sigma, which gives us lower ground motions and low return periods, but this comes at a cost. We must fully capture the epistemic uncertainty in the side term. So capturing this epistemic uncertainty in the side term becomes very important. So again, we'll go back to what are the repeatable effects. In the ergodic case, we capture the uncertainty in the side term. The epistemic uncertainty in the side term is implicitly phi S to S, is the variability of the side terms across the network. In partially non-ergodic, we must capture what is the epistemic uncertainty in each of these components that we use to predict side response. Okay. I can summarize then the role of side response in PSHA as predicting what is the repeatable side term. In fact, predicting what is this site-specific deviation at the site of under analysis from what would be the predictions of a ground motion prediction equation. We can do these two ways, using recordings, which almost never happens. It's very rare that you will have sufficient recordings to capture that at the site for a range of magnitudes that are of interest for hazard. Although it's possible, you can select study sites where this is the case. What you can rarely do is that these sites would be sites that are of interest for the placing of critical facilities. But nonetheless, it's theoretically possible. We can use predictions as a function of site characteristics. If we use predictions, it's important that these predictions include the epistemic uncertainty in the site term, which can be, if you're using recurrence, it's simply statistical uncertainty. With predictions, you have to properly account for all sources of uncertainty. You can see the estimation of the epistemic uncertainty in the site term as the cost of reducing the sigma. So this will be the cost of doing a partially non-ergodic PSHA. And one thing that I would like to highlight is that site response goes beyond what we geotechnical engineers traditionally think of site response, because it relates to all the effects that are not captured by the path in the GMP, which means that typically it goes to much larger depths because there is variability at depth that's also impacting the side effects. And also important, what we are doing is a relative side response, relative from the target to the host, the target being the site under analysis, the host being the site condition that would be characteristic of the ground motion prediction equation model that we are using. So our site response would be a relative site response between the target and the host. Okay, so what is the epistemic uncertainty in site response? So how can we capture it? No. Again, if we look at the uncertainties that we have to consider, we will have now uncertainties in the host profile that relate to the properties of the host profile. We'll have uncertainties in the target profile that include the profile, the VS profile, density, small strain damping, usually estimated by the attenuation parameter kappa. Uncertainties in the nonlinear behavior and the modulus reduction and damping curve. If Professor Stocky were still listening, he would be very much interested in this because he has contributed significantly to the understanding of the nonlinear behavior of solids. It's uncertainties in how we account for spatial variability in randomization, and there are uncertainties that are related to the simplification of going from a multi-dimensional problem to a one-dimensional problem. There are also model uncertainties, and we have to make a choice between doing modeling 1, 2, or 3D. We have to make a choice between modeling approach, where it's equivalent linear or nonlinear, using a random vibration theory versus time series analysis, and we need to account for model bias as well. So if we focus on the uncertainty related to the target profile, we have a challenge because it's not clear how to separate aleatory versus epistemic variability. If you choose a site, the site is not a point, it has a spatial extent. And over the spatial extent, there will be variabilities in the velocity profile. If you are simplifying this into a one-dimensional model, then even if you knew exactly what the three-dimensional profile is, there will still be variabilities that are related to spatial variability. In nuclear documentation from the Nuclear Regulatory Commission, there is a document that came out in 2013 that specifies that spatial variability within the scale of a nuclear power plant site should be treated as aleatory variability. So this is randomness in the sense that a wave that's propagating through the site will sample randomly this spatial variability. Whereas epistemic uncertainty should reflect lack of knowledge on the profile. The same document, which is important because it has been used a lot in the nuclear industry, has a recommendation for epistemic uncertainty, and it is to treat epistemic uncertainty as alternative base case profile. And this is a common sense approach that's often also done in typical geotechnical practice. I will expand on this. Aleatory variability will be modeled through randomizations of a velocity profile around this base case profile. And let me expand on the base case profile. Let's pick this sample site where let's say our best estimate of the velocity profile is shown as a green line. We have a sand over rock, we have velocity measurements, we estimate that there is a gradient between the sand and the rock. The rock is over a much stiffer basement rock. However, we have uncertainties on the profiles, and a typical approach is let's bound these uncertainties and let's create an upper bound profile and a lower bound profile as shown in here. And typically, these are scaled to account for the uncertainty in the measurements. And if you do side response analysis for these profiles, you will get uncertainties, you will get amplification factors with respect to the base that look like this. But note, you can identify points where these amplification functions are crossing. These crosses would imply that if we use only these profiles to account for epistemic uncertainty, at this oscillator period, the uncertainty, the epistemic uncertainty is reducing to 0. But this is not real. this is simply an artifact of using a discrete number of velocity profiles and characterizing the uncertainty simply through shifts in the velocity profile. You can construct cases where, as the uncertainty increases, the hazard decreases. This was done by one of my PhD students. You have here a low and a high epistemic uncertainty case, and with the high epistemic uncertainty case, your modes spread out more, and as a result, you end up smoothing the amplification peaks, and you can end up, if you convert it into hazard, with lower hazard for high epistemic uncertainty, which is counterintuitive. No, it's saying, okay, the less I know, the lower my hazard would be. An alternative approach is to be much more rigorous in characterizing all sources of uncertainty in the velocity profile through a logic tree. We do this already for source characterization, or for ground motion models. We should do it as well for side response. This means that you account unseparated for uncertainty in velocities in the soil. These uncertainties are typically uncorrelated with uncertainties in the velocity in the rock. Okay. You may have uncertainties, let's say, in the thickness of different layers, or you may have uncertainties in the damping or in the modulus reduction and damping values curves that you use for the soil. If you could also include host profile uncertainty, because remember, we must do side response relative to a host profile. If you do this, and you do side response analysis, now you don't have simply 3 curves, but you have a family of curves, typically in the order of hundreds of thousands, which are represented by the gray lines in here. And after you do this, you sample this uncertainty, but no longer sampling it in the parametric space that is input to the side response analysis, but now sampling it in the amplification function space. This resample uncertainty captures now all the range of amplification function or side response that is represented in the side response logic tree. But the key difference here, because the concept is simple, and probably many of you have used a logic tree for side response, but the concept that I'm trying to push, or I'm trying to emphasize here, is that we are resampling the uncertainty on a space of amplification function rather than on the parametric space that is input to the side response analysis. So we do this sampling on amplification function space rather than what typically is done in shear wave velocity. And you can do lots of neat things with this approach. You can create what's called tornado plots. These tornado plots take different branches of the logic tree and compute conditional means for each of these branches. And then you plot the resulting hazard for each of these branches. And you can sort these from higher variability to lower variability, which helps identify what's contributing most to uncertainty. For the sample that I showed before, at low oscillator periods, what contributes more to the range of uncertainty is the uncertainty in small strain damping, followed by the uncertainty in the soil velocity. At 1 second, damping doesn't have as much of an influence, but the uncertainty in the velocity, in the shear wave velocity of the soil, has the biggest contributions to uncertainty. Another way of looking at it is variance contribution. This comes from a different example, but this tells you which branch or which node of the logic tree is contributing most to uncertainty. In this case, we had uncertainty in the method used for side response analysis, or in the profile, in the velocity profile, or in the transition from the surface to deep velocities, shear wave velocities at depth, etc. Kappa is uncertainty in damping, and you can see for different frequencies what contributes most to hazard. For example, in this particular case, if you look at high frequencies, uncertainty in kappa, which is damping, has the biggest contribution. If you look at low return periods, let's say at 1 second, now the biggest uncertainty is on the biggest contribution to uncertainty is on the VS profile. So you can use this approach to understand your problem better. Okay, one important additional contribution to epistemic uncertainty is the uncertainty of in model error. So the basic assumption we do in model in site response analysis, typically, at least we geotechnical engineers do, is assumption of one-dimensional wave propagation. We have vertically propagating, horizontally polarized shear waves. You have horizontal layers of infinite extent, and you have the base of the profile is a fully absorbing boundary condition. So it's an elastic half space. Okay. This is typical in our 1D approximation, but these assumptions are not always realized. There is parametric uncertainty in all the input parameters, and there is uncertainty in the simplification to 1D site response. When we do the site response logic tree, we capture parametric uncertainty. However, we know there is also uncertainty related to the model. This is typical. This is the epistemic uncertainty implicit in logic tree. This is from a particular project, but this is typical. At high oscillator frequencies, the parametric uncertainty leads to high epistemic uncertainty or the implicit uncertainty in the logic tree. At low oscillator periods, it does not. But we have evidence that there is uncertainty also at long periods. If you look at networks that have surface and borehole recordings, such as the KickNet network in Japan, you can see that at low periods, you have large site-to-site variability. You also can infer this from studies of downhole arrays. And that's because of model error. So how do we incorporate model error? There's two ways that we can do it. We can add model error as an additional uncertainty component. That means an additional branch in our site response logic tree. But this implies that the model error is uncorrelated from all other sources of epistemic uncertainty. The second alternative is you impose model error as a bound, as a minimum bound on the epistemic uncertainty, which accepts the correlation between the estimates of model error and the parametric uncertainty that's embedded in the logic tree. So this means that you impose a minimum epistemic uncertainty, which means that your range of fractals from the hazard that you sample from the amplification function has to be spread out to reach this minimum level of epistemic uncertainty. What is this minimum level of epistemic uncertainty? One estimate can be made from looking at the KickNet network in Japan, where you have surface and borehole records. And the borehole records are typically very stiff material, where if we were to use one-dimensional site response analysis, would predict no amplification. Yet the variability from site to site is about 0.22 ln units. So this is an indirect estimate of what the model error is. A more direct estimate can be done using downhole arrays, and different people have come up with different estimates. A recently published study by John Stewart proposes a model that's here shown in dashed lines using downhole arrays. A separate study, unpublished by Walt Silva, proposes a much lower model error of about 0.1 in ln units. Recent work by one of my PhD students has taken look at this problem using the KickNet array, and rather than using surface to borehole ratios, we use the site terms in a prediction equation, in a ground motion prediction model, and we use a Bayesian approach to obtain model error. The results are a function of how much parametric uncertainty we assume. For reasonable values of parametric uncertainty, we get these orange curves. And just to highlight here, these orange curves are much lower than the model by Afsharian Stewart that I mentioned before. And in fact, the value average across periods is about 0.22, so consistent with what we obtain in the KickNet study. So to conclude, because I know I'm close to my 40-minute time limit, site response logic tree is meant as a way to capture epistemic uncertainty in site response, and it should include all sources of epistemic uncertainty. You can use visualization approaches like the ones I showed to trim out branches of the logic tree or nodes of the logic tree that don't contribute to uncertainty. The weights in the logic tree should reflect the analyst's confidence that the given value represents the true value. And importantly, we should account for model error either as a minimum epistemic uncertainty or as an additional branch of the logic tree, and a stable estimate of model error. An average estimate is about 0.22, although it has variations with frequency that should be accounted. With this, I conclude my presentation. Again, thank you very much to the organizing committee. And as Professor Stocky mentioned, we don't do this in a void. So I also extend my thanks to multiple graduate students that have worked with me over the times in developing this work.
Thank you, Professor Rodriguez Marek. Yeah, open for questions. And I request the audience to put your questions in the QA box. And if any of the panelists do have questions, please do ask.
There is a question in the chat box. In the chat. The question is related to the convolution approach. Should we consider full sigma for the bedrock reference hazard or remove the side-to-side component? The answer is not straightforward because, okay, you should remove the S2S component. You should consider single stage sigma, but in that, if you do that, your median estimate of the side response has to be computed, and the epistemic uncertainty should be computed as well. If you are not doing this, it means that you are computing your mean side response effects using a GMPE, and your epistemic uncertainty is your S2S. So if you're not entering additional information in a side response analysis, then you should use the full sigma, including the S2S. Now, but if you are putting additional information, then you should remove the S2S, but incorporate then the epistemic uncertainty in the side term. I hope that's clear, but it's a good question and it's an important question. And the key is you should remove the S2S component, but you can only do that if you're then placing or putting epistemic uncertainty in your mean estimate of the side term.
Sorry, I have a follow-up question for the answer you just gave. So when you say that we have to consider S2S in the site response, so you mean to say that we do amplification function, we fit an amplification function, so obviously we get a median site response, and then we can calculate the S2S. So you are suggesting that we have to deduct this from the total sigma and use it in the convolution approach.
Yes, I mean, if you're doing site response and you compute an amplification function, then you should also compute what's the epistemic uncertainty in this amplification function, and you should incorporate this epistemic uncertainty in your PSHA. But if you do this, then the aleatory variability that you use in your GMP should be the single station sigma.
Okay. Yeah, that answers my question. Thank you.
Thank you. Yeah, any other question?
Yeah, can I?
Please.
Thank you, Professor. Professor Adrian, it's a very interesting presentation, and always PSHA is very tough to understand. And you started very nicely explaining the basics and all. I just have one curious question. You said when there is more uncertainty, your error parameter estimation is coming down. Okay, when there is less uncertainty, it is more. In common sense, by common sense, it appears it should be other way. So what is your take, please?
Well, what I said, just to clarify, is you can construct cases for additional uncertainty leads to lower hazard, which is not good. No? That's why this would result only if you are using a very crude approach to trying to capture epistemic uncertainty. meaning that you are only, let's say, using this approach of scaling shear wave velocities, you could end up with the case in which you have this pathological case of lower hazard for higher epistemic uncertainty, and that should be avoided. And we could get into philosophical discussions as to why in some cases that could be the case, but in general that should be avoided. And a way to avoid that is using the approach that I indicate, in which you are more rigorous about capturing uncertainty by using capturing all the uncertainties in side response within a logic tree approach.
Thank you.
Any other question? Yeah, please, Dr. Indrajit Paul.
Yeah, Dr. Adrian, is very, that PSHA and DSHA is very close to my heart actually during my PhD studies, but couple of years I'm slightly changed my domain to the governance. So while understanding your domain area, I mean, it's really interesting. You're doing a lot of things on the nuclear power plant, and that is one of the critical infrastructure. And we're also working on some other critical infrastructure in the energy infrastructure, especially. So I was curious to know, like, while you are doing the PSHA and especially for the site response, and there is a large amount of uncertainty, but in case of the critical infrastructure, you had a huge amount of investment involved in selecting the site where it will be constructed. So in that context, what is your suggestion? Like, how much uncertainty we should take a risk of investing that amount of money, because any CI or critical infrastructure having a huge amount of investment. So in that context, what will be the confidence level of the model we're talking about? And the second link to that point also, while considering the seismic part, so are you also considering the maximum credible earthquake for that particular locality, where we are working for the seismic velocity and the seismic hazard assessment for that particular location?
Okay, so if I interpret your question, the first part of your question correctly, is why are we using a probabilistic seismic hazard assessment in lieu of considering deterministic approaches in which we are considering a maximum credible earthquake? I think there is a false dichotomy that the probabilistic approach negates or negates the deterministic approach. In reality, in a probabilistic approach, you are considering all possible earthquakes, including a maximum considered earthquake, maximum considered ground motion. The difference is that in the probabilistic approach, you are also assigning, you are weighting all those scenarios by the probability that these scenarios would occur. So the problem with deterministic approach is that you are putting essentially all your weight on a single scenario. And whereas the typical thinking is, well, this is the worst case scenario, in reality, there are possible worst scenarios that exceed that maximum credible earthquake. So in probabilistic analysis, you take into account those larger scenarios by giving them lower weight. So I would say that the primary reason for doing probabilistic approach is that it creates a rational way of deciding what level of ground motion to use. Whereas in the MCE approach, in the deterministic approach, there is a choice that's made a priori of what this worst case scenario that precludes necessarily worst earthquakes, and often doesn't account for more frequent earthquakes that by virtue of occurring more frequently can result in higher hazard. And that choice is not always made with statistical rigor. It's often based on a large degree of judgment. In probabilistic analysis, we shift that judgment to selecting what's the hazard level that we want to choose. Now, as to the second part of your question is, how do we account for uncertainty? Well, I think that's what differentiates, that's what makes for a good PSHA, how to properly account for all the uncertainty. And In critical facilities, that's done through an expert elicitation process, where the task of the expert panel is to capture what we call the center, body, and range of technically defensible interpretations. And I would claim that the best way of doing this is by trying to follow some type of rigorous expert elicitation process that involves process of integrating, of evaluating all possible interpretations of data and models, and then a process of integrating all this information into a model that tries to capture all this uncertainty. And I don't know if there's a magic recipe for this, but in the US nuclear industry, there's a process called the SHAC process that postulates such a process, you know, to try to capture this answer. I hope I answered your question, but feel free to send me an email if you want to elaborate.
Understand why DSHA, sometimes we are considering like extreme cases, right? That's why. Yeah, thank you for the explanation.
Yeah.
We have few questions in the chat box as well, in the Q&A.
Just quickly to add, I have just followed.
Yeah,
can I ask quickly? Yeah, means if I rightly understood, like PSHA may provide in some cases maybe worse scenario as compared to DSHA. Am I right?
Yes, in some cases it does. In fact, if you look at the seismic hazard map in the US, PSHA has led for near fault scenarios to much higher ground motions than deterministic approaches. So it depends. In some cases it can be lower, in some cases it can be higher, but definitely there are cases where it can be higher.
If it is lower, should we go with the DSHA or PSHA?
I don't think so. If you have a PSHA that's rigorous or conducted, and so you can argue, you can make an argument that you want to go to ground motions that corresponds to lower frequencies of exceedance. You know, if for reasons that are not related to the seismic hazard in itself, but if you have a target exceedance, let's say 2% in 50 years, and that's your regulatory target, because let's say you have a target, you want to restrict probability of collapse to a certain level, then I see no reason to choose deterministic approaches if they give you higher values, because those values that are the deterministic approach are giving you corresponds to probabilities of exceedance that are much lower, which it means that you are, if you have no reason to try to target lower probabilities of failure, then there is no reason to go for a deterministic casing.
Thank you.
I'm a strong believer in the probabilistic approach because it can lead, the choices should not be made deterministic or probabilistic. The choices should be made, what level of hazard do you want to accept? No, and that comes from the probabilistic approach.
And probably based on the level of confidence on the analysis that we are doing.
Absolutely, and that's why you have hazard fractals, and you can choose then. It's okay, if you want to be more conservative, then you don't use the mean hazard, use a certain fractal of the hazard.
I'm not there in the figure.
Thank you, Professor.
Yeah, Adrian, can I ask a last question? Quick one, very quick one.
Please, sir. Please.
Thank you. Thank you. I just have a very quick question. So when are we going to graduate to do the probabilistic analysis in liquefaction?
That's a very good question. I'm gonna tout one of our own work, our own papers, but we published in 2020 a paper on the probabilistic analysis of liquefaction for the Groningen site in Netherlands. The lead author is Professor Russell Green, who is a colleague at Virginia Tech, where we have done a very rigorous probabilistic analysis of liquefaction. So I think we are there. It's just that it's not a common approach yet. But I think we should start doing it. I think we have the tools. We have demonstrated in Groningen. I think that was a very nice study, that a publication in the Journal of Geotechnical Engineering of I.I.Sc. But I think we should move that way.
Yeah. Thank you. We have started that. That's why I asked that question. Thank you.
Okay. Yeah, if by chance there is no other question, maybe we already have exceeded our time. Therefore, I request Dr. Indrajit Pal to summarize. And from my side, I thank the organizers. We had 2 excellent lectures. I felt really honored to listen to both these lectures. And thanks to the organizers for giving us the opportunity to listen to as chairpersons of the plenary session. And over to Dr. Indrajit Pal to summarize and end.
Yeah, thank you. I think it's a nice discussion in both the cases, like for Professor Adrian and also Professor Kent. So we had 2 different dimensions. We have listened from 2 experts, and then the first one, Professor Stoke. So he mentioned about like mostly about the shear wave velocity and different methods, how SASW are useful for the practical purposes. So also, I think we have seen at least about 7 to 8 examples from different sites. And also we have got some sort of information on the how it can be practically used. And it's a nice discussion also in the end as a how it can be used for the monitoring system. And the second one, now, Professor Adrian, also we have nothing to elaborate too much because we discussed also a lot on the PSHA, especially the probabilistic seismic hazard assessment. That's one of the sort of discussion. And right now, I think most of the countries having almost need and some extent develop a certain resolution of PSHA. But I think still there is a lot of work to be done on the microzonation using the PSHA for many of the seismic active countries. But I like 2 extremely 2 interesting factors where Professor Adrian mentioned about the 2 different approach for the uncertainties and also the decision tree. And lastly, the discussion also ended up with the possibility with the intervention of Professor Sitaraman, like how we can expand this activities to the PSHA towards the liquefaction. We also believe, and there is also discussion with the PSHA and DSHA, what is good and what is bad, but I think both are the things important, and we had a different dimension for both the approaches. So with this brief, I'd like to thank both the excellent keynote speaker and also thanks to the organizer for inviting these excellent speakers and as well as a nice discussion. Thank you so much.
Thank you very much.
Thank you, Professor S.K. Prasad and Dr. Indrajit Pal. On behalf of organizing committee, we thank you both for nicely conducting this session. And we also thank Professor Adrian and Professor Stokoi for taking out their time in odd times and making presentation. It's really very wonderful and educative. Thank you one and all. I request Professor Sitaram, Chairman, if he want to say any final concluding remarks.
No, thank you. I think every session I should not come. It's all right. So but first of all, thanks to both the speakers, Kenneth Stokey as well as Adrian, for an excellent lecture, and I really enjoyed, and also very lively discussion. And I started liking this platform so that I can do my work also as well as listen to lectures. Thank you so much. Namaskar.
Thank you one and all. See you all tomorrow morning.
Thank you.
Tomorrow morning,
Bye-bye.
sorry. Tomorrow morning, those who are interested in yoga session will start at 7:15 in the plenary hall. Okay, please join.
Thank you.
Thank you. Thank you.
And tomorrow evening, 6:30 is the cultural program, which will be a sort of a retreat of Indian culture, particularly Bharatanatyam and also Hindi songs, which is Bollywood. And in addition to that, there are some children also playing some dances and programs. Thank you.
Thank you. Thank you so much.
Thank you.
Okay.
Thank you.
Good night.
Yeah. Thank you, everybody.
Thank you very much.
So, Ravi, are we joining on the other link?
Yes, sir.
Not join, sir.
Yeah, I will join the other.
Thank you. We will leave and rejoin on the other link. Thank you.